I think it just makes more sense to talk about all of the limit information at one time and not split the limits into two chapters split apart by derivatives. I just think it fits better here. And so I pulled section 4.6, not all of it, but most of it, I pull over into chapter 2. So what are we going to be dealing with here? We're going to be dealing with two basic types of limits. One of them is called an infinite limit, and the other one is called a limit at infinity. So these are different things. So infinite limits and limits at infinity. Infinite limits are constants divided by 0. In other words, these are your vertical asymptotes in the graph. All right, those are your vertical asymptotes. Now, what about a limit at infinity? What is a limit at infinity? So this is section 4.6, and I split it. This is part 1, the bigger part. A limit at infinity is what happens to the graph as x goes to the far right or far left?
End behavior?
End behavior, exactly. So if you've learned that term before, end behavior, limits at infinity are exactly what we're talking about. They're end behavior. And infinite limits are vertical asymptotes, or they just go to infinity. All right, so I'll show you a couple of different types. And let's see if I still have that graph in here, if it'll work. No, not that one. Let's do, yeah, that looks good. All right. So I've put on here a rational expression, a rational function. It's the ratio of two polynomials. It's got some zeros in the denominator. One of them would cancel because x squared minus 5x minus 6 factors as x minus 3, x plus 2. And so because it factors, I actually have a hole out here at 3. Let me see if I can find 3. Where's 3? I may have to come down. Where is 3? Wow, it's like way up here. Still haven't gotten to 3. Dadgummit, where's 3? Okay, I can't get to 3. All right, well, you're just going to have to trust me. There's a hole up there at 3. All right. Great. So we have this various behavior going on. We've got x minus 3, which is, or actually, I made a typo. That should be minus x. Now I've got my hole at 3. There we go. I can get right on it. Oh, come on. There we go. I have a hole at 3, all right, because I have a factor that cancels x minus 3. And then I have a vertical asymptote at the y-axis because x can't be 0. And I have another one here at 1. All right, so I have some various things going on here. So I have some really bizarre behavior in this graph. So a vertical asymptote is an infinite limit because the graph is going to infinity, all right, at a finite x value. Now I can also have something similar happen if I turn this one off and I just put on a regular old graph. Oops, how did I get down there? There we go. All right, so if I have something like this, I still have what's called an infinite limit, but this one is an infinite limit at infinity. As x goes to the far right, the graph goes up forever, but it's not a vertical asymptote. It's still an infinite limit. It's still going towards infinity, but as x goes to infinity. So I can have a combination of the two. I can have an infinite limit at infinity. I can also have an infinite limit at a vertical asymptote. And then I can have a constant limit at infinity. So if I look at this one, do you see how the graph is approaching the x-axis? That means as x is going to negative infinity, the y value is approaching 0. So I have a finite limit as x approaches negative infinity. So I have these different ideas of, do I have a vertical asymptote that would be an infinite limit as x approaches a finite value? Do I have an infinite limit as x approaches infinity? That would be like on the parabola. Do I have a finite limit as x approaches negative infinity? That would be like this rational function approaching 0 as x goes to the left. Or do I have an infinite limit as x goes to negative infinity again? And that would be like the parabola going off to infinity as x goes to the far left. So we have different combinations of these, and that's what we want to focus on here in section 4.6. Infinite limits where the y value goes to infinity, and limits at infinity where the x value goes to infinity. So y goes to plus or minus infinity, and limits at infinity, x is going to plus or minus infinity. So that's the difference between the two. All right, an infinite limit is talking about the y value going to infinity, and a limit at infinity, the at means x is going to infinity or negative infinity. Okay, so we've talked about most of these. Let's talk about limits at infinity and horizontal asymptotes. So what happens as the function goes to the far right or the far left? Do we have a horizontal asymptote? Like we saw in the previous graph, x approached the x-axis, right? Y approached the x-axis as it went out to negative infinity. And that's a horizontal asymptote in the graph. Now, horizontal asymptotes can be crossed by the function. In fact, it can wiggle up and down across it infinitely many times. The one that can't be crossed is the vertical asymptote. A horizontal can be crossed, but a vertical cannot. The horizontal is a tendency for the graph to do something. The vertical asymptote is thou shalt not divide by 0. Therefore, you can never touch or cross a vertical asymptote. The graph can't do it. So when we write something like 2 plus 1 over x, and we look at the figure right here, this is the graph of 2 plus 1 over x. All right. And when you're looking at this, and of course you could write it as a common denominator, and that would give you 2x over x. That would give you 2x plus 1 over x, right? Same graph. If you're looking at this graph, do you see how it approaches the y value of 2 as the graph goes to the far right and as the graph goes to the far left? We call this a horizontal asymptote because it's drawing in the y values, but on the end behavior. And by end behavior, we mean the ends of the picture, all right? The far left and the far right. So the end behavior on this one is that it has a horizontal asymptote at 2, all right? And again, horizontal asymptotes can actually be crossed. It could come up and do something like this where it gets closer and closer and closer as it goes out to infinity. And it's fine for a horizontal asymptote to be crossed, all right? It doesn't cause a problem. Thou shalt not divide by 0, though, means vertical ones cannot be crossed. Okay. You can tell by looking at a graph, for example, on the table. You can also tell that it's approaching the value of 2. I'm not going to spend a lot of time on those because they're pretty obvious from looking at them. And the limit then is L, all right, or M, depending on whether you're coming from the left or from the right. That's the horizontal asymptote. Now, what we do want to talk about is we want to talk about how do we know that we have a horizontal asymptote? What is there in the function that we can algebraically determine we have a horizontal asymptote? It's easy to tell from the picture, even on this one, which is cosine of x over x plus 1. You can tell it has a horizontal asymptote. It is doing what I said, where it's oscillating above and below the asymptote. But do you see how as it goes out towards x is positive infinity, it wraps the line tighter and tighter. And so it becomes a horizontal asymptote at y equal 1. And this is the end behavior to the right. So we would say that the limit as x goes to positive infinity of cosine of x over x plus 1 is equal to 1, because it approaches the y value of 1 as it goes to the right. So the limit is talking about what the y value is doing, and below the limit, this is talking about where x is while that's happening. All right. All right. So if we're looking at each of these and you're wondering where it goes, you can do the same sort of thing. On this one, I would use graphs in order to determine it as we go to the left and to the right. So we want to look at 3 plus 4 over x. So let's put those on the graph. All right. So we want to look at the graph as it goes out to the far left and the far right, and you can adjust this a little bit. It looks to me like it's approaching a value. All right. Does everybody see that? It does look like it has a horizontal asymptote. How can I determine what the horizontal asymptote is? Algebraically, the best thing to do is to get these written in common denominator form so that you have 3x plus 4 over x, and this is your function. Now, what's happening as the numbers get massively, massively large, and we're talking about, way, way far right and way, way, way far left, the numbers themselves are massively large, either positive or negative, but massively large. What difference does adding 4 make when you get out to that massively large? Well, it's like a grain of sand on a beach. 1 grain of sand on all of Miami Beach. Tiny, tiny, tiny. It does make a difference, but it is minuscule. So as x goes to infinity, this graph approaches a different graph. This graph approaches the graph of 3x over x. Because as you get to infinity, let's say you're at 1 billion, then you have 3 billion plus 4. I mean, what difference does plus 4 make? It might as well be 3 billion. So you have 3 billion divided by a billion, which is practically 3. So this becomes the horizontal asymptote of 3. So what we're doing is taking the highest degree term in the numerator and dividing by the highest degree term in the denominator, and noting that it reduces to 3. And when you look over here on the graph, if we graph y equals 3, you'll see that it is the horizontal asymptote on the far left and the far right. It is what it is approaching as you go far left and far right.
I have questions. I always have so many questions. So can we see it instead of like having x as the same denominator? Can we see that when 4 or like constant is divided by like a really big number, it's gonna be close to 0?
That's right. So as x gets larger and larger, 4 over the larger and larger number goes to 0, so it approaches 3. Same idea. All right, so you can do it either way. You can do it this way or you can do it from this form. Later on, most of them will be written in this form, which is why I cover it now. But you can tell these pretty easily from this form. As x becomes a billion, then a trillion, then a quadrillion, 4 divided by that is so small, it's practically 3. But practically means not exactly. So it's approaching, it's a limit value, right? So it's a limiting value. So what we want to start talking about here is infinite limits at infinity. So the infinite limit is referring to the y value. So the first part refers to the y value going to infinity. When it says at infinity, it's referring to the x value going to infinity. So an infinite limit means y value goes to infinity. At infinity means x is approaching either infinity or negative infinity. So when we have this situation, we write the limit as x approaches infinity or negative infinity goes to infinity. And we have lots of graphs that we know about that do that. For example, the most obvious one is just your upward opening parabola. So when you have an upward opening parabola, as x approaches infinity, as it goes off to the right-hand side, then the value of y also goes up forever. And as x goes to the far left, the y value goes up forever. So this is an infinite limit at infinity in both directions. If they go to negative infinity, like they would in a downward opening parabola, then we still have an infinite limit at infinity. It's just a negative like this, right? So again, we have as x approaches the far right, the y value is going down towards infinity. And as x goes to the far left, again, the y value is going to negative infinity. So these are still called infinite limits at infinity. All right. Now, if you have a graph like x cubed, you can have one of each type, where as x approaches the right side, it goes up towards positive infinity forever. And as x approaches the left-hand side, negative infinity, the y value goes down forever. So in one like this, we would write the limit as x goes to negative infinity of x cubed equals negative infinity. And that would be this left-hand side. And on the right-hand side, we would write the limit as x approaches positive infinity of x cubed is equal to infinity. Now, technically, that means they both do not exist because infinity is not a finite real number. All right. Okay, you can see that as well by looking at some of the values that you get when you allow the x value to get larger and larger. As x gets larger and larger in magnitude, or smaller and smaller as it's negative, you can see that the y values are getting larger and larger in magnitude as well. Okay. We'll be doing the formal definitions of these in the next section, which we'll cover tomorrow, which is going to be 2.5 after we finish 2.4. All right. So the next thing we want to talk about is end behavior of a function. We've already been talking about this a little bit. Infinite limits at infinity are end behavior, but we want to define it a little bit more precisely. So there are different types of end behavior. You could be approaching a horizontal asymptote, y equal L, or it could be an infinite limit at infinity, or it could just not approach anything. It could have some kind of oscillatory behavior. So let's draw a picture for each one of these. This one would be something like where it comes up and then it approaches some value out here, and it approaches some value out here. So those would be two different horizontal asymptotes at infinity. And this one would be like the graph of x cubed, where you would have an infinite limit at infinity. And the last one would be like a sine or a cosine graph that has some oscillatory behavior, and it never settles down to approach just one finite real number. Sine and cosine go between -1 and 1, and so they never settle down and approach a single value. And so they oscillate, and we say they have no limit. We want to talk about in behavior for polynomial functions. We'll start with the polynomial power functions. Polynomial power functions are single-term polynomials that have real coefficients and a whole number for the power. So it could be 0, 1, 2, 3, et cetera, except we usually start with 1. The others, we tend to just call them constant functions, right? When you have x to the 0, you get 1. And so that makes it a constant function. So we're going to be looking at the power functions here, which are single-term polynomials, and talking about what happens to them as x goes to infinity or negative infinity. So we'll start with this one right here. This one is a series of even power functions. All right, so when we're looking at these are all even power functions. And you can tell that they all take on the basic shape of a parabola, except as the power gets higher, they get flatter near the origin and they get steeper in their climb. All right, so they go up steeper. And the teal colored one on the far outside is, of course, the parabola x squared. And then x to the 4th is this orange red color, and x to the 6th is the dark blue color. And you can tell as x goes to positive infinity, it goes to infinity. And as x goes to negative infinity, it also goes to infinity. Now, we also have odd ones, which would look like these right here. These are your odd power functions. And when you're looking at the odd power functions, they have, in some ways, the basic shape of x cubed. Even the line x has this behavior that it goes down to the left and up to the right. So it's approaching infinity as x goes to infinity to the right. It's approaching negative infinity as x goes to negative infinity to the left. And again, x cubed and x to the 5th have the same basic shape, but x to the 5th is flatter for a longer period than the graph of x cubed is, and then it climbs more steeply than x cubed does. But they have the same basic shape. So when we're looking at these up here, we can say that as x goes to positive infinity, they all go to positive infinity. But as x goes to negative infinity, the even power functions, which is the first set right here, they go to positive infinity, and the odd power functions go to negative infinity. And that's because a negative raised to an odd power is still negative, and a negative raised to an even power is a positive. Okay, so let's do an example right here. We want to know what the limit is as x goes to positive infinity. So the first thing we want to do is identify that it's an even power function because it has power 4 on it. But the second thing we want to identify is that it has a -3 coefficient. So this is going to make it go up 3 times faster, but it's also going to reflect it over the x-axis. So we're going to have a reflection. So the basic shape of this is going to be much steeper. And then it's going to get very flat, and then it's going to come back down again, something like this shape right here, right? Where it's approaching the origin right there, right? That's not a bad picture for me, okay? So looking at this one right here, as x goes to positive infinity would be x is going to the right. What's the y value doing? The y value is going towards negative infinity, which technically means it doesn't exist, but we still write negative infinity because it gives more information. Now, what happens if we add in more terms for the polynomial function and not just look at a power function? Well, it turns out that it's only the highest degree term that determines the end behavior. And you can think of that highest degree term as having all the power. So the a to the n, x to the n, the highest degree term in the polynomial function is the one that determines the end behavior. So this is because as you go to larger and larger x values and you raise it to higher and higher powers inside the polynomial, the highest power is going to have a multiplicative effect on the value of the function. And so it's going to have the greatest effect. Now, in textbooks, it may not be the first term written, so be careful about that. They may write it as the second term, but don't be fooled. Go through your list and find the variable x with the highest power on it. That is the highest degree term. All right. So yes, they're just trying to trick you, so don't fall for it. All right. Now, why does it only depend on the highest degree term? If I take this polynomial that I have right here, a sub n, x to the n, a sub n minus 1, x to the n minus 1, blah, blah, blah. This could be something like, we'll just make it simple. We'll make it 2x to the 7th plus 3x to the 6th minus 5x to the 5th plus 4x to the 4th minus 3x cubed plus 2x squared, I ran out of room, plus 7x plus 42, all right? 42 is always a good number. Okay, so a sub n is 2. The highest degree term is the 2x to the 7th because 7 is the highest power that we ever have on x. Remember, there are two conditions to be a polynomial, and I will ask this on exam 1. What are the two conditions to be a polynomial? The first one is real coefficients. The second one is whole number powers on the variable. And that's 0, 1, 2, and 3. All right. So those two conditions are the conditions to be a polynomial. I will ask that on the first exam. All right. And if too many people get it wrong, I'll be asking it again. Okay. So 2x to the 7th is our highest degree term. And what we want to do is we want to factor out the x to the 7th, all right, which is what they're doing right here. So they're factoring out the highest degree term, and what happens is it leaves a fraction behind. So if we take x to the 7th and we factor it out of that, we get left behind a 2 plus 3 over x minus 5 over x squared plus 4 over x cubed minus 3 over x to the 4th plus 2 over x to the 5th plus 7 over x to the 6th plus 42 didn't have any variables, so it's over x to the 7th. So when we factor out that highest degree term, all the ones left behind except the highest one, except the first one, they all become fractions. And they all become fractions with x to a power in the denominator. Now, as x gets larger and larger in value and goes to infinity, what's going to happen is that all of these are going to go to 0. As the x value gets larger and larger, it drives the fractions down to 0. All right. And so we end up with just the highest degree term. That's basically what's happening. All right. Okay. So that the limit of the function becomes the limit of the highest degree term. And I often will write that like this by saying that the limit of f of x approaches the limit as x goes to positive or negative infinity of a sub n x to the n. In other words, the further out you go, the more closely it approaches the graph of the highest degree term power function. All right, so we're going to take an example, and we're going to look at the example and show you how this works. So we're just going to look at a simple one, 2x squared plus x minus 6. If we're at a value close to the origin, say 1, which of the terms is the most effective as far as the y value goes? Well, if I plug in a 1, I get 2 times 1 squared, which is 2, plus 1, 1, minus 6. Well, it's the constant term that has the most effect or the most power on the value. As x gets larger and larger, though, or smaller and smaller to negative infinity, it's the 2x squared that has more power. So let's consider a relatively small value of x equal 1,000. Now, we don't think of it as small, but it is small in the grand scheme of things. When you're thinking about values that go to infinity, 1,000 is relatively small. So if I take 1,000 and I square it, I double the number of zeros. So I get a million. Yeah, so I get a million times 2, which is 2 million. So the first term becomes 2 million. The second term is still 1,000, and the last term, the constant term, is negative 6. Now, which term has the most effect or the most power? It's definitely the highest degree term, which is 2x squared. All right. So this is what we mean by as the x values go to the extremes, the end behavior of the function, the highest degree term has the most power or the most effect on what the graph does. So it has what I would call a limiting effect. So when I look at these right here, this is going to be a graph where first I'm going to identify that's the highest degree term, negative x cubed. So I know that as x goes to infinity, this is going to approach the graph of negative x cubed. All right. It's not going to be exactly equal to it, but it is going to approximate it. So when I get out there, it's going to do what the graph of negative x cubed would do. Now, the graph of negative x cubed kind of looks like that. Okay, that's not really a very good picture. Let's see if we can make that one a little better. Okay, so coming down, coming through, and then coming down. Slightly better. So as x goes to positive infinity, the y value goes to negative infinity. So the graph up here is going to approach negative infinity. And then as x goes to negative infinity, it's going to go to positive infinity. Let's take a look at this graph on Desmos. Let's see if I can get Desmos to come up. All right, move this over here. And we are looking at that function right there. Take that off. So let's look at the graph of negative x to the third minus 3x squared plus 4. All right, so here's our graph right here. And I'm also going to graph the asymptotic graph, the one it approaches, which is y equals negative x cubed. All right, so what's happening is that near the origin, when the values are relatively small, they're not alike at all. They're very different. But as the values go out towards infinity, they'll get closer and closer together. So as we go further and further up, the values are going to get closer and closer together. It draws in the graph and it becomes like an asymptote, right? And they approach each other, okay? And that's what happens. Now let's talk about the end behavior for rational functions. Now, remember, for a polynomial, we have two conditions, and I do expect you to have this memorized. The conditions to be a polynomial are 1, real coefficients, and 2, whole number powers on the variable. And that would be numbers like 0, 1, 2, 3, 4, and so on. And then what is a rational function? Well, a rational function is easy if you know what a polynomial function is. A rational function is the ratio of two polynomial functions. All right, so you need to know the definition so you know when you can apply which rule. All right, so we're looking at the ratio of two polynomials. So we have real coefficients in the numerator, real coefficients in the denominator, whole number powers on the variable in the numerator, whole number powers on the variable in the denominator. So when we're looking at this, we know that for polynomials, it's the highest degree term that dictates the ends behavior, the far right and the far left of the graph. And so when we're looking at that, we can assume then that as we have a rational function, the ratio of two polynomials, that the end behavior is going to be dictated by the highest degree term in the numerator and the highest degree term in the denominator. And that's exactly what happens. So it's the highest degree term, the one with the highest exponent, that affects what the graph does. So when we look at these, we need to identify which one is the highest degree. And then we're going to examine the comparison of the degree of the polynomial in the numerator with the degree of the polynomial in the denominator. So we're looking at this expression right here where we have a sub n x to the n over b sub m x to the m. So let's suppose our highest degree term on top is that, and our highest degree term on the bottom is this. So this is the ratio of the highest degree terms. All right. So when we're looking at the ratio of the highest degree terms, this will determine what the end behavior does. If n and m are equal to each other, then we have a horizontal asymptote, because if n and m are equal, then the variable parts will cancel out and we get the ratio of a sub n divided by b sub m, and that becomes our horizontal asymptote. So the horizontal asymptote is a sub n divided by b sub m. Now let's suppose that actually the power in the denominator is larger than the power in the numerator. So for example, this could be an x squared over an x to the fourth. So the denominator power is larger than the numerator. So it will cancel all of what's in the numerator, but still have some power in the denominator. And because it still has power in the denominator, it's going to drive the entire function down to 0 as x approaches infinity or negative infinity. Right? And then what happens if instead it's top heavy and n is greater than m? So let's say we have x to the fifth on top and x cubed on bottom. Well, 3 of the ones on top will cancel the 3 on bottom, but we will still have x squared on top, which is going to pull the graph towards infinity or negative infinity, depending on what the original powers were. So there won't be a horizontal asymptote. Okay. I sometimes call this the Bill Gates rule or the Jeff Bezos rule. The person with the most money tends to control or rule over what's going to happen. So that's kind of where that comes from. So let's look at this one right here. Take a few moments and think about it, and think about what the graphs must look like. You may want to graph it on Desmos if you want to, see what it looks like, and determine what you think the end behavior will be. So by end behavior, that means I'm looking for the limit as x goes to positive infinity of f of x. And I'm also looking for the limit as x approaches negative infinity of f of x. So take a moment to think about that, and then we'll share our answers. All right, so what do you think we're going to get as our limit as x goes to positive infinity of the function 3x squared plus 2x minus 1 over 5x squared minus 4x plus 7? What is going to be the limit? Anybody want to take a guess?
Horizontal asymptote at y equals 3/5.
That's correct. So we get a horizontal asymptote at y equals 3/5 because our highest degree term is 3x squared in the numerator and 5x squared in the denominator. So it approaches the graph of those two, and those reduce to 3/5, which means that the limit on the far left is the same, which means that this particular rational function must have a horizontal asymptote on the far left and the far right of 3/5. So let's graph it real fast and see what we have. So we have y equals 3x squared plus 2x minus 1 divided by 5x squared. Oh, and I'm not typing. My bad. Okay, let's start over. Y equals 3x squared plus 2x minus 1 by 5x squared minus 4x plus 7. All right. Okay, so this is kind of an interesting graph. Scroll in a little bit so we can see this one. It does this weird sort of dip here near the origin, but as we get out towards the edges of the graph, it is approaching the line y equals 3/5. So we can graph that line y equal 3/5, and we can make it a dotted line if we want to, so that you can see it's the horizontal asymptote. And the interesting thing about this one, I think, is that it's approaching the horizontal asymptote from above on the right-hand side, but it's approaching the horizontal asymptote from below on the left side. Does everybody see that? It's getting closer, but from below, and this one's getting closer, but from above. All right. Okay. So we definitely do have a horizontal asymptote on this particular graph. Right. This is a really nice example of what one looks like. And I'm looking for my snipping tool, but I don't see it. Let's see. I had it open, but I guess I had closed it. Okay, so we'll take a picture of this and plot it over here. All right, so we definitely do have that horizontal asymptote. Okay, let's take a look at another one. This is one that is what I would call bottom heavy because it has a higher degree in the denominator than it has in the numerator. So think about the three rules that we had up above and decide what's going to happen as x goes to positive infinity of this function and what will happen as x goes to negative infinity of this function. What do you think is going to happen? Your highest degree term in the numerator is 2x. Your highest degree term in the denominator is x squared. So the ratio of highest degree terms becomes 2x over x squared, which approaches 2 over x. So what's going to happen as x gets massively large? X, and I think this was plus 1 over x squared plus 6x plus 5. It's going to approach 0. So our asymptote is not going to be 3/5. It's going to be the x-axis. It's going to be 0. So you can see the behavior of this one, and it is also doing a very similar thing to the last one. It's approaching the x-axis from above to the right, and it's approaching the x-axis from below to the left, but it is going to approach the x-axis. And the reason is it's bottom heavy. And because it's bottom heavy, that means that it's going to tend to go to 0. All right. So the limit on the far left and the limit on the far right agree, they're going to go to 0. So if they have even degrees, it approaches a horizontal asymptote. If they have more on the denominator than in the numerator, they are going to go to 0, and it still has a horizontal asymptote. All right. What about this one? This one's different. You have x cubed as the highest degree term on top, and 3x is the highest degree term on the bottom. And the ratio of highest degree terms is going to be equal to x cubed over 3x, which becomes x squared over 3. But as x goes to infinity, it's going to follow the shape of that particular graph, x squared over 3. So our limit as x goes to positive infinity of the function should go to infinity, and the limit as x goes to negative infinity of the function should also go to infinity. So my guess is that they're both going to go to positive infinity because x squared reaches up on both sides. Let's check the actual graph and see if that's what it does. So I have x cubed plus 4x squared plus 3x. Over 3x plus 9. 3x plus 9. Oops, wrong place. 3x plus 9. There we go. All right. In fact, it follows it very, very closely. Does everybody see that? And we can graph, what was it, x squared over 3? Like that. And you can see that it's going to approach it as it goes out towards infinity. It follows the path of the arms as the arms get higher and higher. Close to the origin, they're not the same at all. But as it gets closer and closer to infinity, it does approach the other graph like an asymptote. All right? Sort of draws it in and does what the other graph does. Okay? Let's take a look at another example. All right? Who wants to volunteer to guess what this one is going to do as it goes to infinity and negative infinity? Any volunteers?
Is it a horizontal asymptote at 1?
Yes, it is. So Cherie is correct. We have a horizontal asymptote at 1. The ratio of the highest degree terms is going to be x squared over x squared, which is going to reduce to 1. All right, always make sure that you're finding the highest degree terms, and remember the textbook may hide them and not put them in descending order. And because these reduce to 1, that means we have a horizontal asymptote on the far left and the far right of 1. Okay, so if you were to graph those, the further out they go, the closer to 1 they get. In towards the origin, they probably won't look like that at all. All right. So we've got x squared. I guess I could just delete this whole thing. So we've got x squared plus x minus 2 over x squared minus 3x minus 4. Okay. So, and we'll close that one. All right, so looking at this particular graph, and we want to graph y equal 1. All right. Did I put that in correctly? Oh, I've got 43. That might affect it some, but not a lot. But, ooh, quite a bit. Interesting. Okay, we'll take a look at that one next because that one's almost more interesting than the one we do have. All right, so I'm going to scroll out so we can see this one. Does everybody see that it does eventually settle down and get close to the value at 1? All right. And when I had 43 in here, it was a lot further off, but it still is going to approach the value of 1. All right. Now, it's got an asymptote out there at 43, but if you scroll far enough out, you can tell that it's still approaching 1 on the left, and it's still approaching 1 on the right. It just added in an extra vertical asymptote at a value it cannot be. All right. So no matter what you have, if the ratio of highest degree terms comes out to be a constant, that constant is your horizontal asymptote. Okay. Let's now switch our focus and take a look at what happens within behavior for functions with radicals. Now, the textbook does not really cover this, so don't expect to find this in the textbook. This is in my notes, but it's not really in the textbook. So we're going to cover it because I always put these on exams. I always put these on exams. That's a major hint, right? You should be starring these pages, put a paper clip on the page or something. This will definitely be on the exam. So we're going to start our discussion by talking about what the square root of x squared is equal to, and it is not x. All right. In high, I know, Aubrey's eyebrows went up. What? In high school, you're taught that the square root of x squared is x. It is only x if it is non-negative. It's actually the absolute value of x because you don't know if x is a positive number or a negative number. Let's think about this. If I took -3 and I squared it and I put that under the radical, I'm not going to get -3 out. What am I going to get out? 3. Yeah, I'm going to get out 3. All right. So you have to be careful when you don't know anything about the sign of the variable. Now, how did they get away with this in high school, always telling you that the square root of x squared was x? In the directions, which you never read anyway, it said, assume all variables are positive values. But you never read that, so you kind of missed that part. If you don't make that assumption, then the square root of x squared is the absolute value of x, which is a piecewise defined function. It's x if x is not negative, greater than or equal to 0. And it's the opposite of x if x is negative, because a double negative, -3, would give me a +3. So that's what they're doing when they put the negative on the x in the bottom. They're saying the x itself is negative. So if I put another negative on it, I get a double negative, which will make it positive. All right. So that's where the rule is coming from. So the square root of x squared is the absolute value of x. And I have been known to put that on the exams as well as to what the definition is. So as x goes to infinity, and you've got something like 4x squared minus 3x plus 9 under here, it is still true that the highest degree term has the greatest effect. So it's still up to 4x squared to dominate and determine what's going to happen. So this is going to approach the graph of 4 x squared, but that's going to be 2 absolute value of x. Does everybody see that? Which means that as we go to positive infinity, the values are all positive. And as we go to negative infinity, the values are all negative. So we have to multiply by a negative. That's going to change things. So if we're going to positive infinity, we're going to get 2x as x goes to positive infinity. And we're going to get negative 2x as x goes to negative infinity. All right. So let me pause there and give you a second to kind of absorb that. All right. So again, the highest degree term dominates, which is the 4x squared. The square root of 4 will still give us 2, but the square root of x squared is the absolute value of x. As x goes to infinity, the values are eventually all positive, right? Infinity is far right, so it just becomes 2x. But as you go to negative infinity, eventually the values are all negative, so you have to put a negative on the front, right? So this is going to change what we get when we put it into a ratio. All right, so let's take a look at this particular value right here. We've got the square root of 4x squared minus 3x plus 9 over x minus 21. This is as x is going to infinity. So we know that we'll get the positive value, right? So this in the numerator is going to approach the square root of 4x squared, which is 2 absolute value of x, which again is going to be 2x for x going to positive infinity, and negative 2x for x going to negative infinity, right? Now, since we're going to positive infinity, we know that it will approach 2x, so that we can replace it with 2x, and the denominator, x minus 21, is dominated by the highest degree term, which is x. So this becomes 2x over x, which reduces and gives us 2. So on the right side, we have a horizontal asymptote of 2. Now, this is not a rational function because polynomials are not allowed under radicals in polynomial functions. All right, remember a polynomial function has a whole number exponent. And by definition, a square root is a 1/2 power, which is not a whole number. And since it's not a whole number, that's not a polynomial. So when you have radical expressions, you can have a different horizontal asymptote on the right from the one you have on the left. Let's take a look at what happens as we go to the left. As we go to the left, we again get 2 absolute value of x, but that becomes a negative 2x, and the denominator approaches x again, which means on the left side, we have a graph approaching negative 2. So we have a different horizontal asymptote on the right than what we have on the left. And here's a graph of the function right here that you can see. It's in red. And I have 2 asymptotes that are graphed. On the top, I have the graph of y equal 2 in a blue dashed line. And on the bottom, I have y equal negative 2 in a black dashed line. And the red is the graph of that radical expression. And you can see that it is approaching positive 2 as it goes off to positive infinity. And it is approaching negative 2 as it goes off to negative infinity. Now, this one is kind of fun in some ways because you can see how the graph goes above the horizontal asymptote and then comes back down and approaches it sort of from below. All right, and this is not an atypical kind of pattern, but it is, I kind of like them. I think they're fun, right? It kind of comes up above the graph and then it comes back down and approaches it from above, even though it originally started below, right? Any questions on that radical expression example? So far, no? Okay. Then let's try example number 8. So take a few minutes, write out what the denominator will approach, and tell me what the limit will be as x goes to infinity. And we'll also do the limit as x goes to negative infinity. As x goes to infinity, what did you get for the horizontal asymptote?
I got 3.
You got 3. Okay, so you had 3x from the numerator. And since it's approaching infinity, that means that it approaches x. So you got 3. What did you get as x approaches negative infinity?
-3.
Negative 3. And that's because the numerator still approaches 3x, but the denominator approaches negative x, which gives you a -3. Let's graph this one so that we can see what it looks like. And I will leave this up here. It's that 3, and we'll do another one. And make it dash as well. And then we've got y equals 3x divided by square root squared plus 1. There we go. All right, so here's our graph. This one is a really straightforward graph. It has this weird kind of, I don't know what you call that. It's like someone swimming almost, except it's more vertical. It's approaching a vertical asymptote in here. It never quite goes vertical, but it gets close. But you can tell it very, very quickly is approaching the asymptote of +3 on the right, and very quickly is approaching the asymptote of -3 on the left. It never gets to them, but it gets very, very close. This is not one that oscillates above and below and wraps it up. This is one that just approaches asymptotically, right? Like an asymptote. Are there any questions over how I know that it becomes x or -x? Are there any questions about this part here in the middle? The square root of x squared plus 1 approaches the square root of x squared, which is the absolute value of x. And that means it approaches x as x goes to infinity, and -x as x goes to negative infinity. All right. Let's take a look at another one. So I'll let you guys work on this one. And I'll write out the basics on top. Okay, let's hear from Brittany, Eric, or David this time. Brittany, Eric, or David, what did you get for the limit as x approaches infinity? This one's a little tricky. Not too bad. Eric, Brittany, David? I'm not hearing anything. You should get 2x over x, which approaches 2, right? So you're getting 2 as x approaches infinity. But as x approaches negative infinity right here, what would you get? You would get a -2. All right, so everybody see that? You have a different asymptote on the left than what you have on the right. So when we look at this one, we would have the square root of 4x squared minus 1 over x plus 2. And our asymptotes are 2 and negative 2. Right? So this one is also kind of an interesting graph. I really like this one. Notice that it's got this weird behavior. Let's analyze, because part of what we're heading into is a chapter in the textbook where we analyze graphs. A lot of chapter 4 is analyzing graphs. Somebody tell me what's happening here really close to the origin, right there. There's no values there. So what's happening there? I mean, there's no graph at all. It's not going below. It's just not there. What's the problem here? If you look at the equations over here, what could be happening in the equation that causes this part of the graph to be missing?
Would that be dividing by 0?
Not dividing by 0, but you're on the right track, Michael. He's looking.
Would that be a 0 in the numerator?
Not a 0 in the numerator. You're all like very close. Not
Negative and square root.
Yes, Jay's got it. You got a negative under the square root. You have a negative value under the square root. So what we've got here is it doesn't exist between negative 1/2 and positive 1/2, because between negative 1/2 and positive 1/2, this turns out to be a negative number, which won't graph on a real graph. So it's just missing, all right? But then the rest of it, you can tell that it's approaching our asymptotes to the left and to the right. So we do want to kind of analyze these graphs and see what could be happening. Remember, you are looking for those two things, 0 in the denominator or negative under a radical. Those two things are the things that are going to cause things not to exist. 0 in the denominator, negative under a radical, right? And later it might be negative inside of a natural log. That can happen as well. Okay. So let's take a look at the next example. 4x over the square root of x squared minus 1. So now that we've kind of got this down, we know that 4x is going to approach 4x. It's a single term polynomial, so it's a power function. The square root of x squared minus 1 is going to approach the square root of x squared, which is absolute value of x, which is going to be x as x goes to infinity, and negative x as x goes to negative infinity. All right. So this is going to give me 4x, and it's going to positive infinity. So it will go to x, which gives me 4. But the limit as x approaches negative infinity will give me 4x over negative x, which would approach negative 4. So when you have radicals, you almost always have two different asymptotes, one on the left and one on the right. There are occasions where they're the same, but it's pretty rare. All right. Okay. And there's the second one. Let's look at one that's got a double radical. All right. So we've got two radicals here. 2 square root of x over x minus square root of x plus 1. Always look for the highest degree term. So the highest degree term is going to be 2 square root of x on the numerator, which is going to approach 2 square root of x. All right. And then in the denominator, what's the highest degree term? This is a little tricky.
The whole x, not the square root.
Yeah, it's the x. In the denominator, it's the x, which is just going to stay x. So as x goes to infinity, I get the ratio of 2 square root of x over x. Can you combine those two and reduce them? You can. It's tricky algebra. And tricky algebra is just code for you got to do some work. Rewrite this as x to the 1/2, and this is x to the first. And that would give you 2x to the 1/2 minus 1, which is 2x to the negative 1/2, which is 2 over x to the positive 1/2, which is 2 over the square root of x. In other words, the square root gets left on the bottom. Now, this is one way of handling it, but I'm going to give you another way of handling it. You could look at 2 square root of x. Maybe I should change colors. Do a little contrast. Over x, and you could consider this 2 square root of x over square root of x times square root of x, because x is equal to its square root times itself, right? So when you take the square root of x and you square it, you're going to get the x if x is going to positive infinity. And then these cancel, and you get 2 over square root of x. Right? But the key to doing that is knowing that x is going to positive infinity, so you're allowed to break it up like that. Right? Now, what is this then going to give me as the asymptote? Or does it have an asymptote as x goes to infinity? How would you reduce 2 over the square root of x? What is it going to approach? Is it top heavy, bottom heavy, or same? I mean, I don't even have an x on top anymore, so it's bottom heavy. So the degree in the denominator is 1/2, which is more than the degree in the numerator. So what's it going to approach?
Would it not have a horizontal asymptote?
Say it again.
0.
Okay, one thinks it goes to 0. What was the other one?
It doesn't have a horizontal asymptote.
I also said 0.
Doesn't have a horizontal asymptote. Okay, so we have a couple possibilities. Let's play a game. Let's put in numbers. All right, numbers that we know are perfect squares, obviously. So if we look at 2 over the square root of x, when x is 1, we get 2. All right, so I'm going to make a table of values. When x is 1, I get 2. My next perfect square is 4. So I have 2 over 2, which becomes 1. My next perfect square is 9. So the square root of 9 is 3, so I get 2/3. My next perfect square is 16. So I get 2 over 4, which is 1/2. All right, I gotta have another table. Let's bump it up really big. Let's go with 100. The square root of 100 is 10. So I get 2 over 10, which is 1/5. Now, to get another perfect square, I got to double my number of zeros. That'd be the easiest. That should be 10,000. All right. So that would be 100. So I'd have 2 over 100, which is 1 over 50. Take a look at those numbers and somebody tell me what you think is happening to the y values.
0.
I think it's going to 0. All right, it's bottom heavy. It's going to drive it down to 0. If the degree of the denominator is bigger than the degree of the numerator, it goes to 0. So let's graph this one so that you can see it. So I'm going to turn that graph off and we'll make this one go to 0. And we have 2 square root of x. Two square root of x over x. Did I do that right? Oh, no, it's +1. Now, did I do it right? Okay. Notice something about the graph. First off, I don't see any graph to the left. Can I do the limit as x goes to negative infinity? No, it doesn't have a graph as x goes to negative infinity because thou shalt not put a negative under a radical, even radical, right? Thou shalt not divide by 0. Thou shalt not put a negative under an even radical. So it doesn't exist to the left of 0. But as we go off to the right, let's scroll it to the left a little bit and see what's happening. As it goes further and further out, it's getting closer and closer to 0. It does take it a while to get down there. Notice that it's actually not getting there very quickly. It's actually taking some time and slowly going towards 0, but it does go to 0. That's because it's bottom heavy. And the reason it takes so long is because the degree here of the denominator is a half, which is not very large. The larger the degree in the denominator, the faster it goes to 0. Okay, let me show you an example of that by rewriting this. Instead of writing it as x to the square root, I rewrote it as x to the 1/2. Let me change it. Instead of 1/2, let me make it 1/4. It's going to take longer to go down towards 0. All right, it takes longer to get towards 0. If I made it something like 100, then it really takes a lot longer to get towards 0. All right, so the lower the degree in the denominator, the longer it takes to get to the asymptote. Okay. Now we want to take a look at infinite limits at vertical asymptotes. So infinite limits, again, we're referring to the y value going to infinity or negative infinity. And a vertical asymptote referring to x equals some constant. So we're not talking about end behavior anymore. We're talking about an actual point on the interior of the graph where we have a vertical asymptote and the y value is going to infinity or negative infinity. Okay, now we've already covered these a little bit earlier in section 2.3, but we just want to review them a little bit right here. All right, so how do you know that you have a vertical asymptote? You have a vertical asymptote at x equal a, where a is a 0 of the denominator that does not cancel. So a is a 0 of the denominator in a reduced fraction. So in other words, it doesn't cancel and disappear. If it cancels and disappears, it's a hole in the graph, not an asymptote. I know it's complicated. Rational functions are really very complicated. It takes a long time to master them. And don't worry, because when we come back to chapter 4, we'll be doing exactly that. We'll be talking more about it. Okay. So if there's a factor x minus a and it cancels completely and disappears, then it's a hole in the graph. Okay. So let me take an example and show you what I mean. Let's say I had y equals x minus 1, x plus 3, x plus 2 over x minus 2, x plus 3, and x minus 4. All right. Now, does one of those factors cancel and disappear completely? Yeah. And it would be the x plus 3, right? So there is a hole at x equal negative 3. Because the factor x plus 3 disappears completely and is gone from both numerator and denominator. Now, what about the two that are left in the reduced denominator? I have a vertical asymptote, which I'll abbreviate VA, at x equal 2 and another one at x equal 4. All right. So I have a vertical asymptote at x equal 2 and one at x equal 4. So let's take a look at this particular one and let's go ahead and graph it so you can kind of look at the graph and see how the relationship is going. So let's take all that off. So I have -1. Do I have to put x plus 3 in here or not? I do. If I don't, it doesn't realize it's a hole. I have to put it in there as in the original so that it knows it's a hole in the graph. If I don't put it in at all, then it's allowed to be -3. I think I got those in right. Okay, so this is my y value. And then I've got a hole at -3. Where at -3? Now, maybe, how many of you actually studied this in college algebra? Give me a yes in the chat window. If you did not study this in college algebra, give me a no in the chat window. I need to know what I'm dealing with. So I've got some yeses and nos. Another yes. Ooh, I got a lot of no's. Yes, touched on it. Okay. All right, so we're about half and half. All right, so I'm going to assume that you've not seen it before, and I'll teach it to you. So where is the hole? The hole is going to be at the x coordinate, -3, coming from solving x plus 3 equal to 0. And then I put -3 into the reduced fraction. So I have -3 minus 1, -3 plus 2 over -3 minus 2 times -3 minus 4, which gives me -4, -1 over -5, -7. Does everybody agree with my arithmetic? I've got 4/35. Can I get confirmation from somebody? Okay, you're like, Aubrey's like, yes, I'll buy that. Okay, so 4/35 is a hole. So I'm going to graph the point. Oops. Well, let's see if I can even find it. It must be down here. I don't see it. Where was it? No, oh, -3. I'm looking in the wrong place. Duh. Okay, -3, undefined. Does everybody see that? -3, undefined. But I had to put the factor in there so it knows it's undefined. And this is going to be at -3, 4 divided by 35. And it's a hole, so it's not supposed to be solid. It's supposed to be empty. And we are going to label it. All right, so we have a hole there in the graph. We also have vertical asymptotes. We had vertical asymptotes at 2 and -4. So those were the zeros of the denominator that did not cancel. All right, so we have a vertical asymptote at 2, which will put a dashed line, and we have a vertical asymptote at 4, which will make another dashed line. Okay, so we're talking about what happens as the graph gets close to one of these vertical asymptotes. All right, so let me put the graph on here. And I'm going to scroll in just a little bit so we can see a little more of it. Oh, wrong thing. There it is. All right, so as I'm looking at this graph right here, blow it up a little bit. What do you think is happening as x approaches 2 from the left of the function? The limit as x approaches 2 from the right of the function, and the limit as just x approaches 2, the two-sided limit. So let's do that part first. So let's focus on the vertical asymptote at 2. And let's look at what happens as I approach from the left side of 2. Well, it looks to me like it's going to positive infinity. The y values are going to positive infinity. What about as I approach 2 from the right? So this is from the right side of 2. So find the right side of 2, which is down here, and approach 2, but from the right. Well, unfortunately, that looks like it's going to negative infinity. So what are you going to write for the value as the limit as x approaches 2? What is the only acceptable answer?
Does not exist.
Good. Thanks, Juan. Does not exist. All right. And now let's look at what happens as we approach 4. The limit as x approaches 4 from the left. The limit as x approaches 4 from the right. And then the limit as x approaches 4. Do you think you're going to have questions like this on the test?
Yes.
Yes. In fact, you have a quiz on Wednesday this week, and guess what you have on the quiz? Questions exactly like this, right? Where there's no work to do, you just look at the graph. So we're going to approach 4, which is here on the x-axis, but from the left side of 4. So I got to find the graph, which is down here. Approaching from the left, it's going towards negative infinity. On the right side of 4, which is at numbers larger than 4, I got to find the graph in this section, which is up here, and then approach 4, which makes it go to positive infinity. So again, they disagree, so I write D and E. In all cases, the limits do not exist because infinity and negative infinity are not finite real numbers. What's the limit as I approach negative 3? What's the limit at the whole? Come from both sides of the whole. Doesn't it look like it's going to hit the whole?
Yeah.
Then it's the y value at the whole. 4/35. All right. That's what it looks like it's going to hit. So even though it's a hole there, the limit exists. Remember, the limit is what is predicted to happen, not what actually happens. The limit doesn't actually care about what really happens. It's what does it look like is going to happen. That's the limit. Okay. Vertical asymptotes. I think in the first graph, we must have a vertical asymptote at 1. Here we must have a vertical asymptote at -3 and another one over here at 2. Does everybody see how I'm getting where the vertical asymptotes are? I'm looking for where the graph is avoiding hitting a certain value and skimming along the line like it's some invisible force field. In my mind, I always imagine it like in those bad sci-fi movies from years ago. They'd be out wandering in the desert. It was always the desert. It was never a forest. I don't know why. Anyway, they're always in the desert. They're wandering along, and then that's poof, they run into a wall, right? They can't go over it, and they can't go under it. So they have to either walk to the right or walk to the left. They don't have a choice. They can't go over or under it, so they walk along the wall, all right? That's basically what a vertical asymptote is doing. The vertical asymptote represents thou shalt not divide by 0. So you're not allowed to cross it, okay? You can't go over it, you can't go under it. What about this graph here on the left? Where do you think we have a vertical asymptote? Let's hear from Trevor or Camille or Jean. Trevor, Camille, or John, where do you think we have a vertical asymptote in the graph on the left?
Can you hear me?
1 and 2.
No, I couldn't hear you, Sean. So Trevor
Okay.
says negative
Yeah,
1 and
mine is 1 and 2.
Yep. Okay, good. So negative 1 and 2. I agree. All right. Now this one over here on the right is a little bit trickier. What is the value of this one over here on the right?
I think it's 0.
Excellent. Very good. So you're right, John. This one is at x equals 0, which is the y-axis. All right. So we have an asymptote at the y-axis. This is a very interesting graph. Everybody look at this one over here. Do you see how it's coming out like this and it's sort of taking on this weird shape? This probably means that there is an asymptote that's coming out like this on this side and it's skimming along that asymptote. All right, that's probably what's happening. It's called an oblique asymptote in that it is slanted. And we will cover oblique asymptotes in 4.6 part 2. So the second time we come to chapter 4, we'll talk about oblique asymptotes. All right. So now we want to take a look at this one and we want to decide whether or not there's a vertical asymptote at x equal a. Remember, it's a vertical asymptote if it is still there in the reduced fraction. So the first thing you need to do is factor the numerator and factor the denominator and reduce it. Is negative 1 a vertical asymptote in the first function? Or is it a whole? It cancels, so it's a whole. It cancels completely and disappears from the denominator. So it's a whole. So we have a whole at negative 1, and then we plug negative 1 into the reduced fraction, and we get 1/3. So we have a whole at negative 1, 1/3, right? What about this second one? Do we have a vertical asymptote or a whole at x equal 2? It does not cancel. So x equal 2 is a vertical asymptote. All right. If it does not cancel, it's a vertical asymptote. And remember, you are not allowed to cancel part of a term. If it's added or subtracted to something, then you have to put it in parentheses and the whole thing goes or none of it goes. Okay.